this example, we have a beam that has two fixed ends, and of course that means we have three potential reactions at each end, and of course that also means that we end up with then a situation that is indeterminate statically to the third degree. Now, since one of those is in the axial direction and that's decoupled from the shear and from the moment, then we can, for practical purposes, focus here on the shear reaction or the bending reaction, which means it's indeterminate to the second degree. The load is applied in the midpoint, and before we charge off into a lot of theoretical work, let's make some guesses as to what we think these reactions may turn out to be. Before we even go along that path, we need to also make some other assumptions here about we have linear elastic behavior. That's our common typical one. In this case, we have no statement about the EI of the beam, so let's make an assumption that we have constant EI along the length. Right now, it'd be very natural to assume here, and I guess, that with everything being symmetric as it is, that we would end up with our shear reactions just splitting the load evenly between the two ends. What's not so clear is what will happen with our moment reactions. Yes, they'll probably be equal and opposite of each other in direction, but how much will they be? So one thing we might consider doing, again, is just a crude guess, is that goes along, that is, with our assumption about how the load gets split to each side, that the shears end up splitting evenly, but that there's no moment there at the midpoint, which is not going to be a really particularly good assumption, but it does make our life a little bit easier when it comes time to following through on what we think the guesses might be here. So we take the shear, turn it around, that's going to be P over 2. Of course, the shear at the end is also going to be P over 2. And now we've got a moment that can go along with that. That's going to be equal to P over 2 times L over 2, or PL over 4 for our guess at that reaction. That would be a situation that had a hinge in the middle. And so going with our guess, that's the kind of model that would be there. We know that can't be particularly very good in terms of what happens in the midpoint, but maybe it works out not so bad on the ends. We shall see. But that at least gives us some sort of sense of what's going on. This also helps us to think about what might happen with the shear diagram, that it would look something of this nature and be symmetric, where we split that load evenly between the two ends. Now, we could draw the moment diagram that goes along with our assumption of the hinge in the middle, but since we think that that's not really very realistic, we might go ahead and jump ahead slightly, and that is thinking about what we think the deflected shape might look like, that we'd have some sort of zero slope at the middle because of the symmetry. We'd have concave up or smiley face in the deflected shape here in the middle portion, and then at the ends then we would have frowny face to accommodate no rotation at the ends. If that's the case, then we should end up with a moment diagram, given what our shear diagram is, that would look straight line or triangular in orientation, with negative moments at the end, positive in the middle, and it's not necessarily clear what we're going to end up with for the maximum values or in the end values, but we've got to guess that maybe the ends might be negative PL over 4, probably less, right? Because negative PL over 4 would mean we'd have 0 in the middle. That would correspond to here, and so we expect us to get then something at the end that is less than, between 0 and PL over 4 at the ends. Right, with that, that gives us then the background or the setting to go do some theoretical work.